All right, so we're going to do number 2 here, where we have this 860 Newton crate, and it's asking how much work is required to move it at a constant speed along the floor, and how much work is required to move it at a constant speed vertically. One of the key understandings to have here is that work is only done when the force and the direction of the distance, that's kind of a weird statement, but the direction of the distance are in the same dimension or in the same directionality. It's a strange statement because distance is a scalar, so how can it have a direction? What we're really looking at it as distance is the magnitude of the displacement. If you look at our equation sheet, we didn't really touch on this because some of you different math levels here. We have our third work equation, which actually has the vector, the force is a vector, which it is, and the displacement here, and they're dotted together. A dot product with a vector means I'm taking and multiplying the scalar parallel portions of those vectors together. There's 2 ways to multiply vectors. Cross product, where you combine the perpendicular parts, and dot products where you multiply the parallel parts. A dot product gives you a scalar, not a vector. It doesn't have any directionality. Cross product gives you a vector in a new direction. We are not going to talk for a while. We may talk about that and some other things. So we're going to that's why I have to say that kind of weird statement of the direction of the displacement. So in your Y, it would be good to show that you understand that work is done when the force, I'm just going to use the, and distance are in the same direction. Same direction. And work's only done when that's true. In this case, we look at this case, in A, the force and the displacement are in opposite directions, but they're still parallel to each other. And since it's a scalar, we're still going to get a positive value, but realize that work is going to take energy away from the crate, not give it to the crate. That'll become important as we move down the line. In the second one, we don't know if it's moving at a constant speed up or down, so it could be either way. So we're just worried that we have a displacement and a force that are parallel to each other, not whether or not they're opposite each other. So this would be one of the key understandings. I might expand on there just to show, because this is kind of generic, show I really get this problem. So the weight, that's the, does work vertically, and friction does work horizontally. That's really bringing it down to saying, hey, yeah, I get the overall concept, but I also understand how to apply it in this problem. So that's, remember, you want to always show your reader of your Y that you understand how that, an overall principle applies to the problem at hand. So the equation that I'm pulling from my equation sheet, I'm going to use that work is force parallel, the distance parallel. And for A, my force is 180 newtons, and my distance is 6.7. So 180 newtons times 6.7 meters. I double check, I have it in newtons and meters, which means when I get my answer here, I can either put it in Newton meters or joules. looking, they want joules. So my answer, a Newton times a meter is a joule. And then for B here, now it's the weight of my object doing the work. Weight of my object is 860 newtons. And again, it's moving at 6.7 moving for 6.7 meters, and I will get an answer in joules because it's newtons times meters. So let me know if you need help individually on any of the problems or on this one, and I'll be glad to come around and help you individually.